So we're going to work the first example from the conservation of momentum examples together. In this example, which is an example of an explosion, we have two lab carts, one of mass m right here, and the other of mass 2m, which are initially at rest. At rest is kind of an important thing to note. On a level frictionless track, we then release a plunger between the two of them, which pushes them apart, such that the m cart has a velocity of 2v to the left. So first of all, I'm going to refer to the m cart as being cart number 1. And I'm just going to go ahead and draw that guy right there. And it's moving at velocity 2v to the left. So I'm going to draw an arrow like that, indicating that that velocity is 2v. And I want to call that something, I could say that that's velocity of cart 1 after the collision. It's like, or after the explosion, rather. The superscript prime can be used for afterwards. The other one, which is heavier, is probably going to move to the right, and it's probably not going to go as fast. So I'm going to draw a smaller arrow. I'm going to call that V2 prime. That's one of my unknowns that I'm going to be asked to solve for, so for right now I'm just going to call that question mark. So the first thing that I'm asked to do here is to analyze the motion of the center of mass of the system. Draw a dot showing the horizontal location of the center of mass of the two-cart system. Label this Cm. So because the cart on the right is a little bit heavier, the center of mass is probably going to be shifted towards that cart. So the center of mass would not be right in between the two, it would probably be a little to the right. I'm going to label that Cm. So that's step A. Draw a picture showing how the carts are moving after the explosion. I've done that. The second one will probably be going slower than the first one since it's heavier. Done that. On the after picture, draw a dot showing the horizontal location of the center of mass of the two-cart system. So now I want to figure out where's the center of mass over here. And the key thing to remember is that the center of mass velocity is constant. So because there's no external forces, whatever that dot is doing before the explosion must be true after the explosion. Well, that dot's not moving beforehand, so afterhand, that dot is going to be in the exact same place that it was. In other words, if I had this track balanced on a pivot right here, and I push those two carts apart with that plunger, they would not tilt the track in either direction. It would stay pivoted. So remember that the center of mass velocity is constant because there's no external forces. That's the key thing to remember there. All right, so part D, derive an expression for the final velocity of the 2m cart, that's cart 2 in my picture, and indicate its direction. Well, I'm pretty sure that it's going to move to the right, but let's figure out how fast it's moving. The first thing I'm going to do is define right to be my positive direction. Then I'm going to calculate the momentum of the entire system. I'm going to say P system. And I'm going to do that using the information in the before picture. I don't have enough information to do that over here. Well, this one's real easy. The M cart is moving at 0 velocity because it's at rest. The 2m cart is also moving at 0 velocity because it is also at rest. And so the momentum of my carts together is 0. Because momentum has to be conserved, that's also going to be the momentum after they explode. So over here, I'm going to say that the momentum of my system afterwards, that's what the superscript prime represents, is equal to m times 2v, so momentum of the blue cart. Remember to make that negative because it's moving to the left, and I define right to be my positive direction, plus 2m, that's the mass of this one, times v2 prime, which is my unknown, that's what I'm looking for, and all that has to add up to 0 because that's the momentum of the system, and the momentum of the system is conserved. So simplifying this a little bit, that'd be negative 2mv plus 2mv2 prime, which is what I'm looking for, has to equal 0. So now I've got that equation, it's just a matter of solving for that unknown. So v2 prime, add the 2mv to both sides, divide by 2m to get v2 prime by itself, and we end up with v2 prime just equals v, because the 2 cancels out and the m cancels out, leaving just v on that side. And I know from my picture that it is moving to the right. So all I've got to do there is figure out how much momentum my system has, write an equation using that momentum. So I know what this is doing. I can figure out what this is doing because the momentum stays constant, and then just solve for my unknown. The last thing we're asked to do is figure out the kinetic energy gained by this two-cart system. Remember that the equation for kinetic energy is K equals 1/2 mv squared. So to find the kinetic energy of my system, I'm just going to take the kinetic energy of cart 1. So it's 1/2 m times 0 squared, and add it to the kinetic energy of the second one. All right, well, that's really easy. The kinetic energy of this system is initially 0, because neither one of them are moving. 0 and 0 add up to 0. Afterwards, they're both moving. So I'm going to find the kinetic energy of my system afterwards just by doing the same thing, only using the after velocities instead of the before. So that's 1/2 times m times 2v squared plus 1/2 times 2m times v squared So my kinetic energy of my system afterwards, well, 1/2, 2 squared is 4, that'd be 2. And then plus, well, half of 2 is just 1. So that gives me a kinetic energy of 3mv squared. So I started with 0. I ended with 3mv squared kinetic energy. So the kinetic energy gained by my system is just 3mv squared. And that, everybody, is the end of the first example.